Have you ever wanted to go back in time to sneak some different colors into Van Gogh's palette? If so, I'll admit that's a little weird, but that means you're in the right place. This video is for you. Stay tuned. Hi, my name is Chris, and welcome back to my OpenCV and C# series. This is the second video in the series, and if you missed the first one, the link is in the description below. In this video, we're going to cover some image manipulation techniques that you can easily do with OpenCV, including resizing and rotation, changing colors of individual pixels, and even applying our own convolution kernels to transform the image in some, well, interesting ways. So if you're someone who wants to understand the basics of OpenCV and Emgu and wants to be able to digitally manipulate images, stick around. And let's get started. Okay, before we dig into the more flashy stuff, let's discuss some basic resizing and rotation functions in OpenCV. And as always, we're going to be using our Starry Night JPEG. If you want this JPEG or the source code from the last video or this video or future videos, the GitHub link will be in the description below, and you're looking for the OpenCV tutorials repo. So let's get started, and we will start with creating a new mat, and we'll name it pick, and then we're just going to go ahead and invoke ImRead. I am read. By the way, the I am image, if you didn't put that together, I don't think I even said that in the last video, but it's what it is. So we're gonna pull in our JPEG. Okay, so now pick is Starry Night. And then let's go ahead and make another one called resized pick, and we'll just set that to default initialization. That's fine, doesn't matter. So to understand sizes in images in OpenCV, the thing to understand here is, if you think about what an image is, it's a bunch of data, and each pixel in that image is at a location in the two-dimensional shape of the image. And if you think about how you would necessarily access each individual pixel, you would do a row and a column, right? Just like you would a two-dimensional array, for instance. And in our case, the x values of this two-dimensional array, the x values would be the width of the image, right? Also known as the columns. I know it might be a little weird to say that, but the columns are the width, because if you had, say for instance, you had an image that was 50 columns big, if you think about what that means, if you add 5 more columns, now it's 55, you've expanded the width, right? Because you've added columns, so the width gets bigger. The inverse of that, or it's not really inverse, but the rows are the same thing, but for height, right? So if you added 5 rows to an image, you would add 5 pixels to the height. So images in OpenCV are accessed through width and height, and what we're really talking about here are rows and columns. So just to show that, we'll get our height from pick, and we'll access this rows property. And same thing for width, and that would be the columns property. Okay, and we can display this just to kind of, as an example, we'll just say Starry Night is, and then height x width. Okay, all right, let's run this, make sure it runs. Okay, and it's a little hard to see on the video, I'm sure, but it gives us our height. It's 899 by 1135. So there you go. That's the size of our image. All right, so now we know how to access the size, but for right now, we're going to resize the image, and the way you do that is with a function, a built-in function called resize. And its parameters, as you can see in this little tooltip here, there's an input array of pick, there's an output destination array, or a mat, in our case that's resized pick, and then this third option here is called a size. It's an object called size, And actually that's from the system.drawing.size. It's the system.drawing namespace. And so we're just going to create a new size object, and here you would give it your pixel size. And I believe it's width, height. So let's do 400, 500. Yeah, width, height. So this is going to take our image from pic. It's going to place it into the resized pic image, and it's going to have size 400 by 500. Okay. All right, so then now we need to display those. And we'll use our ImShow function again. And so we'll display the original. And then we'll just call this resized tonight. Okay, and don't forget, if you're going to show, you want to do a wait key. Otherwise you will miss the windows when they pop up. So, all right, so if we run this, we then see our resized images, or image. So here's the original, and here's our resize. So that's 400 by 500. So with 400, so you can see the width is smaller than the height. And obviously, just it may be clear, but this title bar does not count inside of this sizing. That's just added on top. So, but there you go. That's a resize an image. All right, now we know how to resize an image. Let's talk about rotation. So what we're talking about here is inside of our window, for instance, what if we wanted to rotate the image some amount of degrees left or right, or 180, or flip it, or those kinds of things. I'll show rotation. They're all pretty similar, so if you can do one, you can do them all. But so let's talk about rotation. We got to kind of get through this one before we get to the really cool stuff of color manipulation and convolution kernels. So let's get through this real quick. So basically we need to decide in our rotation example here what kind of angle we're going to rotate. So that's a double, a primitive double type, and we're going to call this angle 45, and it's going to be 45D. Okay. So the way you, well, let me just show this real quick. So invoke dot get rotation matrix 2D. Okay. This is the function we're going to use to rotate. It's got some parameters, and one of them, this first one here, you can see it's called center, and it is of type system.drawing.pointf, or a point floating. And we're going to create one of those real quick. So that's going to be system.drawing.pointf, and we're going to call it center. Okay, and the way we're going to determine the center of the image is through a little bit of math. So in our case, let's do, we have width and height, so let's just use those. So this first one, we're going to do width -1, and I'll explain why in a moment, divided by a floating point 2. Okay, so that's going to be the first argument in this point. And then for the y-axis, we're going to do height -1 divided by floating point 2. So the reason we do -1 here is, again, pic.rows for the height, for instance. Remember, this is giving you an amount of rows, but we're talking about an array, which is 0-based index. So we need to subtract 1 off of both of them to make sure we're aligned in the proper place. And then divided by 2, obviously, it's just the number of rows divided by 2, the height divided by 2, and the width divided by 2. If you combine those together, you'll get the center point. So that's the idea of this this object here. So we pass it the center, we give it the angle, easy enough, and then there's this scale parameter to get rotation matrix 2D, And what that does is it actually allows you to rescale the image in itself. I will say this does not scale the window that you will display the image in. It only scales the image. So we could maybe play with that in a moment, but for right now we're just going to do one. And then it also takes this output array, and we're going to call that rotation matrix. I need to create it real quick, but that's what that's going to be. It's just going to be a mat. Okay. So this will produce our rotation matrix, and the rotation matrix will be used in the next function we call. But basically, it's just building this mat here, this matrix that will pass the information to our next function. So let's go ahead and call that function, and it's called warp affine. And what it takes is an input array, a output array. So we'll call that rotated pick. I need to make that. And then, so let me do that real quick. Okay. And then it takes the rotation matrix. And then it also takes a size. We'll just do this for now. And let's do, I believe it's width height again. I know we just talked about this. Yeah, width height. We'll just use the original because I think it's going to show the best example. Okay, and then so this will take our rotation matrix, apply it to our original pick, and output that into rotated pick. So let's display that so we can take a look. Okay, and since we're done with this example up here, I'm just going to comment this out. Okay, we'll still do the right line, doesn't matter, but all right. So let me run this and we'll see what we get. Okay, so as you can see, it took the original picture, which then rotated it 45 degrees, so from the center. So instead of center line being here, center line is now here. And then we put that matrix inside of the original window, and we rotated it. So you could scale this with that scale factor. If you did a 2, for instance, this would be twice as large. So you would only say, like, you know, this amount of the picture, things like that. So this is how you would rotate. You can do other things as well. If you did a 180 degree rotation here, you would completely flip it upside down, for instance, you know, that sort of thing. So that's pretty much what you need to know about rotation. There's crazier stuff you can do, which we may get to in a later episode. For right now, that basically wraps up rotation. So now let's talk about colors. Okay, let's talk colors in OpenCV. So the first important thing to know about colors in OpenCV is that generally, when you're accessing these colors in an image, they are of the BGR color space. So if you're familiar with RBG color values, you know, each pixel in an RBG pixel, there's 3 numbers. There's the red, the blue, and the green, RBG, and those 3 colors combine to make a specific color. So pure red would be 255, 0, 0. In OpenCV, pixels are BGR, meaning blue, green, red. So it's just important that you know that the numbers aren't in the same order as you might be familiar with. The reason for that is when OpenCV was created, BGR was the standard, but at some point we transitioned to RBG. But OpenCV, we're looking at BGR color types. So let's take in our image. So the other thing to note about this is that you can't access individual pixels on a mat object, on a matrix. what you have to do is you have to convert it to another type, and that type is called image, and it is of type BGR. Oh, not that. BGR, and we'll pull that in a moment, and byte. So let's pull in the BGR. I believe it is Emgu .cv and num, or it might be Emgu.cv.structure. I think it is. I think it is structure. Okay. So yeah, structure. Okay. So we're gonna create a new type. It's a tuple. It's BGR byte, and we're going to name that. Just convert pick. And we're going to take our original pick and we're going to do this function called toImage, and then we're going to give it types BGR byte. Okay, so now what this has done is it's taken our pick matrix and converted it to an image of BGR byte. So now we can do some interesting things with that. I'll say that this is also how you can grayscale an image. There's an object type called gray, and so if we did that, our image would be black and white. So it changes the color space. So for right now, we're going to do BGR because we're going to do some color stuff. And then from here, we want to let's say we wanted to take Starry Night and convert specific pixels if they fall in a certain range. Okay, so we're going to take this new object called image, and we're going to call on convert pick this function called InRange. And what that's going to do is it's going to return an image of type gray byte, and so it's going to be a black and white image, and it's basically the pixel is going to be turned on if that pixel was in our range, and it's going to be turned off if that pixel was not in our range. So how do we give it a range? Well, as you can see from this tooltip, it takes a BGR object. So we're going to make a new BGR, and we'll fill that in a moment, and then we're going to do another BGR. So what range do we want to do? Well, we're working with Starry Night. It's a lot of blue, right? So we can get a good effect, let's change that to, let's the lower end be, say, 75. Okay. And then we'll have the upper end be, let's do anything that's max blue, and we'll just pick some numbers for the other two. Okay, let's try that range. We'll see what that looks like. So now we've got this image. Again, it is bits that are it's a grayscale image, and the specific pixel is turned on if it's in a range, turned off if it's not. So what we can do is we can actually use that to then use that information to do changes to pick. Okay. And well, in this case, convert pick. So we're gonna do some loops so we can iterate across the image. We're just gonna do an I for loop. I'm gonna do across the rows. Oh, I still have the Java the Java curly bracket in my mind. So we're going to do an outer loop there across the rows, and then we're going to do an inner loop here. Okay, so we're going to iterate across the image, and what we're going to do is we're going to look at a specific the specific pixel we're at, and with an image object, the way you can do that is you can actually access it like an array. So we're going to do ij, and then so now we've got the num. It's really the value at that point in the image, and then we're going to do, let's say if the num dot intensity is greater than 0. So if that specific pixel is turned on, then we want to do something. So in our case, I think what we will try is convert pick ij, is equal to, and we'll set it to a new BGR, and we'll change the color. So to get a kind of a cool effect, I mean, you can do all kinds of stuff here. I think one cool effect that I'll show you is you can actually take the current values, right? And the way you access that is with this MCV scalar object. And so what we've done is we've taken convert pick at I sub j, and we're going to take this MVC scalar object, and dot v0 gives us the blue value. Okay, and then convert pick of I sub j dot mcv scalar dot v1 gives us the green, and then convert pick I sub j dot mcv scalar dot v2 gives us the red. Okay, so right now what we would do is we would literally just feed it the same value, right? Convert pick I sub j being a new BGR of the same BGR it is. But let's change it. Let's do some manipulation. So in our blue value, let's subtract 50, just kind of making up numbers. In the green value, let's subtract 50, and let's say we wanted to make it extra red or purple or whatever. So let's increase the red bit by 100. Okay, and so what that's going to do is it's going to take the value that was in there, going to take for instance the blue bit minus 50 off of it, the green bit minus 50, the red bit plus 100. And I think it's worth noting that I think technically we could go below. I don't know if there's any in this picture, but I think technically, since, like, for instance, the green bit, the minimum is 0. So if we subtract 50 from 0, I don't think it'll error. I think it'll just give you back 0 in the value. But yeah, just wanted to point that out because I just thought of it. So, all right, so we've got our convert pick. We've done our manipulation to it. We're iterating through image. Now let's display it. So one thing to point out here, if we want to display it, I believe we'll need another mat, and in this one we're going to take convert pick, and we're going to do the dot mat property on it. So it just takes the image of BGR comma byte and converts it back to a mat, and we're going to store that in change pick. So from here we'll just do the show. Okay, here's the original. And here's our color shifted night. Okay, let me go up here and real quick and get rid of that. All right, so now let's see what this code does. Okay, yeah, so as you can see, it took it's a pretty cool effect. It took any pixel that fit inside of our range, so 7500 to 250 125 125, and then it basically just subtracted 50 off of its blue, 50 off of its green, added 100 to its red, and we end up with this kind of color shifted effect. I'll say doing the values based on the original like this does a much cooler effect. I was toying with it for a little bit, and I would take, for instance, just a hard BGR value, not a variable one, and so you would lose the kind of the color changes in the actual strokes. For instance, you would lose those, and so you would end up kind of like just a glob of paint. It's just all the same color, so that's not interesting. What's interesting is taking his original brush strokes and just shifting the colors on them, so you get all kinds of cool effects. We could also change this to X out of that. We could change this to be for here. We'll just try plus 100 here, so we'll increase the green bit and we'll subtract 50 off the red. Okay, and we'll see what that looks like. Ooh, a little hard to look at, but similar effect. And yeah, we're just making it much more greener. So that is how you change colors on an image. As you start to build these building blocks, you can combine all the things we're talking about into some pretty interesting stuff. For instance, if you've ever seen those image processing programs where you can take an image and, for instance, make the sky blue, or sorry, it should be blue, make it red. Okay, so a lot of those tools will have a thing where you can go out, you can kind of drop color into the sky, it'll change it red, you know, now you've got this cool effect. This is how you could do it. You would need edge detection in that case as well, which we'll talk about in the next video. But I mean, this is just kind of a shifting of pixels, right? So very similar thing. So that wraps up color. Now we need to talk about convolution kernels and how to apply them and the effects you can do with them. All right, so the first thing we need to do here is I'm going to create a kernel, what's known as a kernel. So I'm going to write out this code, talk about it as I write it, and then I will explain this process, this image processing technique. So this is going to be a float array. It's going to be a two-dimensional array, and we're going to call it kernel array. And then, so let's instantiate, and it's going to be a 3x3 array. And we're going to define it like this, just to kind of give some shape to it. It's easier to understand with that shape. Okay, so this is going to be a 3x3 matrix, an array, but it's a matrix. And in it, let's just start with these values, and we'll explain what this is in a moment. -1, then 0, -1, 0. Okay. Just bothered me. Let me line that up. Oh, nope, that has to be minus. All right. Okay. All right. So this is as I said, a three-dimensional matrix, and the idea here. So the process we're going to be using is called convolution, and in the image processing context, convolution is the application of a kernel to an image. And the way it's applied is this matrix, or a matrix. It doesn't have to be this specific one. It doesn't even have to be 3x3. They're usually odd numbers, but anyways. This matrix is applied to each individual pixel in the image. So for instance, if in the top left corner of our Starry Night, it's probably a blue pixel, right? And so this matrix is going to be applied. They're going to do matrix multiplication on the pixel at that location, and the surrounding pixels. And what it's going to do is it's going to multiply each individual number by that pixel, and then they're all going to be summed, added up, and then averaged. And then that value, that average, is going to be put back into the pixel that is being worked on at the moment. And then that kernel is going to slide down one pixel, and it's going to do it again. And it's going to keep sliding down and keep doing this for the entire image, or whatever region you define as your region. So that's what convolution is the application of a kernel to each individual pixel and its surrounding neighbors, as they're called. And then you take that value, you put it back in the pixel, some effect happens. So as you might guess, the values in this kernel will change what effect happens when this occurs. So let's just start with this one. This is a sharpen kernel, the values here, this specifically 0, -1, 0, -1, 5, -1, you know, etc. That is a kernel that is meant to sharpen the image. So if you've ever used image processing software, you've probably seen a sharpen function in that software. This is what it's doing for the most part. So let's go ahead and apply this to our image and see exactly what we can do with that. So the way we're going to do that is there's this convolution kernel F object, and we're going to create one of those, and we're going to pass it our kernel. Okay, and then our kernel array, you know, our matrix. And so we're also going to make a filtered pick mat, and then we're just gonna copy pick to filtered pick. Okay, so now filtered pick is just a copy of pick, and then the way we're going to apply the kernel to the image is through a CV invoke class method called filter2d. There we go. And the arguments, as you can see here, are input array, you know, kind of standard. Output destination. So we're going to do filtered pick kernel, our convolution kernel F, and then a point object. So it's point anchor. The point is another system.drawing.point. It's another system.drawing object called point, and basically this is a point on the image where we're going to be starting. So in our case, we want to do the entire image, so we're going to start at 0.00. That is, oh sorry, I forgot the new keyword. That will tell it just start at 00 and do the whole thing, basically. And from here, all we need to do is show convoluted night and the filter pick, and then we want to invoke wait key just like every other time. All right, and then I'm going to go up here and comment this out. Okay, so yeah, we're going to apply our kernel. We built the convolution kernel from this object here. We copied we copied pick to filtered pick. Just to be clear, the reason we did that, you might think that, you know, the copying really just happens here, but actually filter2d requires them to be of similar types. We're talking about depth space, things like that. And so whatever our pick is, we want filtered pick to match. So the easiest way to do that is just copy them. So, all right, let's go ahead and run this. Okay, and this is our image with the sharpened kernel applied to it. So again, it started in the top left corner, applied this matrix to that top left pixel and the neighbor pixels to it. I should note that in the documentation, it says that if the matrix is applied to pixels that don't exist, so for instance on the edges, the pixels that don't exist are estimated based on its neighbors that do exist. And I'm assuming it's just a copy or something close to that. Of that pixel. So the 0, 0 pixel will be copied out to the -1, -1 and -1, 0 and such. So that kernel was taken, applied to every pixel on the image, and this is what you get. It's sharpened, right? It's kind of a weird example because there's so many different lines and, you know, the brush strokes and everything that goes through all this. So it's kind of sort of hard to tell. It doesn't look good necessarily. But that's the sharpen function. If you were to put this image in, you know, GIMP or whatever and do a sharpen, it's going to do the same thing. It might change the values in here, which would change the effect, but you know, whatever, same thing. Worth noting that we can also just do this multiple times if you really want to get crazy with it. So, but we need to change. We need to change pick to be filtered pick. All right. All right. So now this is applying it multiple times. It's gonna be pretty ugly, but that's okay. Let's see what that looks like. Whoa, geez. Okay, so we have sharpened it so much that there's essentially just tiny lines with white space between them in the image. So it's kind of interesting. Maybe some more modern art, but yeah. So we can apply that multiple times. Okay, let's see. Let's look at another kernel type. Let's do. I have another one here for ridge detection. I doubt this works really well on this picture, to be honest, but we can take a look at it, see what it looks like. So the ridge detection kernel is this. Yeah, all -1s except for the middle, which is 8. And let's we don't want to run this multiple times. Okay, now let's run this, see what happens. So all we've done is change the kernel, change the values in the kernel. Okay, so yeah, you can see that it almost had the opposite effect, right? Of the ridges, areas defined as where there's a significant change in color across 2 pixels, are kind of showing up, and other stuff is not. So it's, again, maybe a little hard to tell in this picture. If we had a picture with less ridges, it would be easier. But yeah, you can kind of see you ended up with a ridge of this structure here, this building. You can see the church steeple, that kind of thing. So literally all we did was change the numbers in the kernel, and you get a very different effect. It's worth pointing out that you can find a few of these kernels on the Wikipedia page for if you just search on Wikipedia for convolution kernel, you'll find the values needed for a lot of those. So yeah, that's convolution kernels. That's how you make your own. You apply them. I'll point out blurs are also a type of convolution kernel. You can do the Gaussian blur we did in episode 1. You can do the same thing here. It's a little more involved because you need to do some math on the numbers. It's not whole numbers, but it's the same thing. You can do a blur in that same way. All kinds of stuff. All right, so we've covered many of the basic image processing types that you can do, such as resizing and rotation, color manipulation, and then we also covered how to apply your own kernels and masking to an image, which is a pretty big topic on its own. Hopefully this kind of gives you the tools to discover more of that on your own. I think you've got the foundation there. So up next on the series, we're going to be going down a path of edge detection, which will be an important step to get to some of the really cool stuff you can do with OpenCV, such as background detection, extractions of an object from an image, things like that. So lots of exciting stuff coming with this OpenCV course. If you'd like to see more of this type of content, please leave a like and subscribe, and I'll see you with the next video soon. Thank you very much. Bye.